Hi guys, I'm making this video to cover the example questions that I haven't been talking about in the last week Wednesday lecture. Okay, so we start with the things in the handout 10 about the heat and heat transfer. Okay, so the topics that we did in handout 10 would be about the heat capacity, would be this equation Qmc delta T. This is how temperature can be changed due to the heating. Okay, and and this equation, the Q equals mL, which L is the latent heat. This equation is used for um, the phase changing. For example, for the LF is the latent heat that used in when your matter is changed from solid to liquid, and this LV, or the latent heat of vaporization, it is used when your matter change its state from liquid to gas. Okay, and the next topic is about the thermal expansion. So the idea of thermal expansion is when you have the change in temperature, your matter, your material will respond to the change in the temperature delta T by changing its dimension or changing its length. So here you have the equation delta L equals alpha L naught delta T. So the change in the size of your material will depend on the original size of your material, will depend on the temperature change, and will depend on the coefficient of the linear expansion, which will vary between the materials. And then we will talk about the heat transfer. So suppose that we have a heat bath of the temperature T1 and another heat bath of the temperature T2. And if we consider the heat flowing from the T2 to T1, the rate of heat transfer, or the dQ by dt, depends on the area, the cross-section area of your medium, and also depends on the distance that the heat transfer, and also depends on the temperature difference between the 2 points. Okay, and the last topic is about the radiation. So, so normally for an object, for example, the sun has its own temperature at the surface, and the sun is radiating some heat out from its surface, and also the rate of the heat transfer, or the dQ by dt, in this case of the radiation, we can calculate from this equation from the sigma, from the epsilon sigma a t to the 4. So epsilon is the emissivity. So if we suppose that your object is the black body, we will have the emissivity equal to 1, and for the sigma, it is a constant called the Stefan-Boltzmann constant, which has the value as showing here. And the A is the surface area of your object, and T is the temperature at the surface. In that case, you will be able to calculate the radiation from anything that has the temperature at the surface. Okay, so we'll start ourselves with the first example. The first example is talking about the energy supplied at a constant rate 1800 joules per second. So this is the unit of watt. So in this case, we're talking about the power. So transfer at the rate of this to 1 liter of water to raise the temperature from 20 Celsius to boiling point. So boiling point is 100 degrees Celsius. And the question is, how long will it take? So how to do it? In this equation, in this question, we start with writing out the power. This is your value of power, and the delta T, or the temperature difference between the initial and final. So you start from 20 and ending at the boiling point 100. So this is your temperature difference at the Kelvin or at the degree Celsius. And then after that, we know that for the water, the CL, or the specific heat in liquid state of your water, is 4.2 thousandths joule per kilogram per Kelvin. And the question is, how much time do we take to boil the water? So, to increase the temperature to the boiling point, we might be considering this equation, QMC delta T. But to get the parameters in this equation, it might not be that straightforward. So from the Q is the heat. So its amount is the total amount of energy, but what we have from the question is the power. So the total heat, if the heat is transferred at a constant rate, or the constant power, we can just simply write down the total heat as the power times by the time, and then equals to m. So the mass, we are not given the mass here, but we know that for the water, so we have been given the volume, so 1 liter. So now what is the 1 liter? So we know that the density of the water is 1 kilogram per liter. So this is the approximation. So the density rho is the ratio between the mass and volume. So mass then can be written by rho V, and then times by the C, and then times by the delta T. So this is all we get from the question. We have P, we have rho, we have V, we have C, and we have the delta T. So that you will be able to find the time. Okay. Then we go to the next question. The graph shows the variation of the temperature with the amount of heat absorbed by 1 kilogram substance. So you just mark that in this example, number 2. Now we have the mass of 1 kilogram. And then if you look at this graph, you have the graph between the temperature and the heat. So if you write down the equation, the relationship between heat and temperature change, again, Q mc delta T. So if we have the plot between temperature and heat, temperature is at the y-axis and heat is at the x-axis. So I can just write down the temperature change as delta T and then 1 over mc times by the heat transfer this way. So this part is going to be the x-axis. This part delta T is going to be the y-axis. And this part 1 over mc is going to be the slope of the graph. Okay, so so you have that when the temperature is increasing, what you have is you have the slope of the graph equals 1 over mc. So in this case, they ask you for the specific heat capacity for solid, liquid, and gas for this substance. So you could simply looking at the slope of these three parts, okay? So we suppose that you have the slope of C for each for solid, for liquid, and for the gas. Okay, so in this case, you can just simply find the C or the specific heat capacity as the 1 over mass times the slope of the graph. Okay, so this is for our part A. And then for our part B, we want to find the latent heat of vaporization, or LV, or latent heat of the fusion, or LF. So in this case, we are going to consider this equation, Q equals mL. And L is going to be the Q over M. So where are we getting Q? Okay, so when we consider the melting of this substance, okay, this, and when we consider the boiling process of this substance, we have the value of heat here, right? So for the melting, if you look at here, the substance started to melt at 10 kilojoule and stopped melting at 30 kilojoule. So the energy that is used this way is 20, right? 20. But and for this case, for the boiling, we start with 50, we stop with 100. So for this case, we use 50. Okay. So this is where we find Q, and you should be eventually find the L, or the latent heat, for the both cases. Okay, so next we go to the another example, the number 3. So number 3 is about to mix the water of mass 2 kilogram at temperature 25 and the water of mass 3 kilograms at the temperature 45. And you want to find the final temperature. Okay, so we start with this is a small water and this is the bigger water. It's 2 kilogram, 3 kilogram. Here I will call this T1. I will call this T2, and also I will call this mass M1, and I will call this mass M2. And what about the specific heat C. We all have this C for the liquid water. The same thing here. C for the liquid water. Okay, so then if you try to mix together the water from these two containers, okay, what happened is the heat from the T2, from the temperature T2, which is 45 degree, larger than the heat from T1, 25 degree. The heat will be transferred from T2 to T1. Okay, so what we can calculate from here is we can write down the equation Q in equals Q out. So here we are considering the heat or the energy that is coming into the colder water. So I write down here the M1C delta T 1. And the right hand side is a heat that is coming out from the T2. So I will write down here the M2 C delta T 2. Okay, so we can cancel the specific heat because it is the same. So that we got the M1 T. So this T is final temperature minus T1. And for the T2, so on the right hand side, I forgot the minus sign here. So what this minus sign here mean is because the heat is coming out, so we write down this minus sign. Okay, so on the right hand side, we have the minus M2 times T minus T2, okay? So in this case, you are given the M1, you are given the T1, you are given the T2, you are given the M2. So you need to do a little bit of mathematics and you should be able to find the final temperature T. Okay? Then we go to example number 4. So how much heat is required to turn the solid ice of mass half kilogram at temperature -5 into the vapor at 100 degrees C? And the specific heat capacity of solid ice is 2000. Okay, so in the last questions, we already know that the specific heat for the water is about 4,200 joule per kilogram per Kelvin. Or you can find the specific heat of the materials here. So this is a value for the liquid water. Okay, so where are we now? Here. Okay. So now we are considering the many step process. Okay, so we start with the solid ice, solid water or the ice, and then after that we have the liquid water, and then we have the water vapor. Okay, but before that, the temperature of the solid ice is increasing from -5 degree from the -5 degree to the melting point of the water, which is 0 degrees Celsius, and then your ice will undergo the melting. After you got the liquid water from the melting, your temperature of water start increasing again from 0 to 100 degrees C, and then your water we will undergo a phase transition again from liquid water to gaseous phase, or the vapor. So this is what we call the vaporization, or I'll just call the boiling here. Okay, so this is a four-step process. So for the first step is we are considering the solid phase of this. Okay, so if I look at the total heat of all the process, so we begin with the first process, the heating the ice, okay, with the same mass, and we use the C specific heat for the solid, and then we use now use the temperature, so 0 minus -5, and then after that we do the Q equals ml. So in this case we use the LF, and then we after we get the water we do the mc delta T again, but now you need to use the specific heat value for the water, and we go from 0 to 100 degree. So now we have 100 minus 0, and finally we go to the Q equals ml again, but now it is going to be the latent heat for the vaporization. Okay, and the mass here, what is it? It's half a kilogram. And specific heat capacity for the solid is 2000 joule per kilogram per Kelvin. And then the latent heat for the fusion, anyone knows what is it? Oh, okay, it is given here for the fusion. It is, so actually they we got this wrong for the handout here. So I think the first one should be the latent heat for fusion, and another one should be the LV. It's the latent heat for vaporization. Okay. So we have the value of LF, 3.34 times 10 to the 5. It is in the unit joule per kilogram. And this is in the unit of 2.26 times 10 to the 6 joule per kilogram. And then of course the C, or the specific heat for the water, it is 4,200 joule per kilogram per Kelvin. Okay, so in this case you should be able to find the total heat, or the total energy you use to melt and to boil the water from -5 degree into the vapor at 100 degree. Okay, so this is the example 4. Okay, so then we go to example 5. Now we we switch to the subject of thermal expansion. Okay, so we start with a very simple one. So we have a rod of the length 2.55 at this temperature, and how much does the rod extend when the temperature is this, and you are given the coefficient of linear expansion. So this is quite easy. What you want to do is just they want to find the, so how much does the rod extend? So this word extend, it tells you that you want to find the delta L. Okay, and delta L here is L0 times the alpha times the coefficient and times the delta T. Okay, and you are given all the values from the question, so you can use the calculator to find the final value very easily. And then example 6. So a solid has the coefficient of linear expansion of alpha, and show that the coefficient of the area expansion is 2 alpha. Okay, so let's do this. Okay, so from just a solid, now we will consider a two-dimensional object. So we can try this with a rectangle. Okay, so suppose that this area, this is the area at the start. We have the area of A0, which is from this side x0 times by this side y0. Okay, and then finally, after the heating, your length x0 will become x, and your height y0 will become y. So in this case, the x, you can find the distance after the heating by x0 times the 1 plus alpha delta t. And also on the other side, you can find the y from y0 times 1 plus alpha delta t. And then if you want to find the area of this rectangle, you can just simply times the x by the y. So this is going to be the area after heating. So A equals xy, and then will equals to x0 times y0. And then will also times by the 1 plus alpha delta t, and times by another 1 plus alpha delta t. So I write down square here. So then A will equals to, so x0, y0 is a0. And we do the complete square here. So we get 1 plus 2 alpha delta t plus delta plus alpha square delta t square. Okay? But normally, what you get, the value that you get from the alpha is, so let's see the order of magnitude here. So the alpha of something like the steel is, so you see the order of magnitude here, it is 10 to the minus 5. Okay? But for your temperature, the order of your temperature is about 10 to the 2, so 100. So it is about 7 order of magnitudes higher than the alpha. And also when you times this together, it will give you the value of alpha delta t about this order of magnitude, 10 to the minus 3. Okay, so we can say that at this point, the alpha delta t is very small value compared to 1. So the square of this term, the alpha delta t, can be eventually cancelled because it is very small. Okay. So what we have left here is the a times a0 times 1 plus 2 alpha delta t. Okay, so if you try to compare this equation to a traditional one with 1 plus alpha delta t, so if you call this the coefficient of linear expansion, or the alpha, so now it is quite fair to say that this term, you can also call this the coefficient of the area expansion. Okay, and so it is proved that the coefficient of the area expansion, just like in the equation, is 2 alpha. Okay, so QED for this. Okay, so now question 7. Okay, you are given the alpha value, and you're also given the C value for an object. So you have a square copper plate of the size 10 and the mass 100 gram, and heated from 0 to 100. So heated from 0 to 100, so you have delta T of 100 degrees C or 100 Kelvin. Then you have the mass of 0.1 kilogram, and you have the area. So I can say it is the A0 of 10 centimeters times 10 centimeters. So 0.1 times 0.1. So it's 0.01 square meter for the area. And then you are given the alpha, and you are given the C for the copper. Okay. So in this case, for the A, so they want to know how much does the plate area increase. So this is what you want to know, the delta A. So you have delta A here as the A0. So times the area expansion coefficient. So this is what we just proved from example 6. So it is 2 alpha, and then times by the delta t. So all are given in the equation. Okay, so you should be able to find the delta A. And then for the B, how much heat does the plate absorb? Okay, so you can start from the increase in the temperature, delta T. Then when you have the mass, and then also you know the specific heat capacity. So you can calculate the heat from Q equals mc delta T again. Okay, so it's not too difficult to find. Then example 8. Now we move ourselves to the heat transfer. Okay, so we start with a basic problem again. So they call that both ends of an aluminum rod of radius r. Okay, so you see the word radius. So that means the cross section of your medium is a circle. Okay, so just don't use the r as the area. Don't do that. Okay, so we used r as the radius, and of course the a, or the cross section area, is the pi r square. And then you are given the length of this, and then you are given the temperature difference, or you are given the delta T. Okay, so you have the L of 0.95 meter, and you have the delta T of 110 Celsius. So what we want to find, so the rate at which heat is transferred. So the rate of heat transfer. So heat transfer is Q, the rate of heat transfer is dQ by dt. Then this will equals to K, so kappa A times delta T over delta X. So our delta X here, the distance is L, so it's just the length of your rod, and the delta T is given here. The A is indirectly given here. And what about the kappa? So the kappa, this is called the conductivity, the thermal conductivity. So this constant depends on the material that you use. Okay, so so here we have the aluminum rod. So what you want to find is you want to look at your table for the value of the aluminum, which is 250 watt per meter per Kelvin. So 250 for aluminum. Okay. So I will call this KAL is 250 watt per meter per Kelvin. Okay, so with this, you get everything. Now you should be able to find the rate of heat transfer. Then number 9, a little bit more difficult, I suppose. So then we have another rod here. So one part of this is steel. Another part of this is copper. And they say that the copper part is 2 times the length of the steel part. So just write down here x and 2x. And then they say that the temperature at this end is 0 degrees Celsius. And the temperature at this end is 100 degrees Celsius. And they want to know the temperature at the junction between steel and copper. So I will be opening the table for you. So for the steel, the conductivity is 46. And for the copper, the conductivity is 401. Okay, so I'll just write down here the kappa steel 46 watt per meter Kelvin. Kappa for copper 401 watt per meter Kelvin. So we consider at the junction. So at the junction, the heat transfer from the steel part here, that should be equals to the heat transfer at the copper part. Okay, so this is the trick for calculating the temperature at the junction. Okay, so from here we can have dq by dt equals to kappa of the steel times the cross-section area, and the temperature difference from the left to the right is 100 minus x, sorry, 100 minus T, when T is the temperature at the junction, and over the distance x. Okay, and on the other side you can use the kappa of the copper times by the area, and the temperature difference from the middle to the right, T minus 0 degrees C, and over the distance 2x. Okay, so here let's see what can be cancelled. So A can be cancelled, X can be cancelled also. Then you have only like 100 kappa steel minus kappa steel times T, and equals kappa of copper times T over 2. Okay, so again you need to do some little maths to get the temperature at the junction. Okay, so then next, example 10. It is about the radiation, so let's read the question very carefully. So assume that the total surface of the human body is 1.2 square meter. Okay, so here if there is a human, yeah, this is human here, just quite like a human. So the surface area here is 0.2 square meter. And they say that the temperature at the surface of the man is 30 degrees Celsius, or it can be thought as the 303 Kelvin. Okay. So the thing about the radiation that you need to know is, for the radiation you need to use the absolute temperature in Kelvin. Okay, don't use Celsius. Okay, just don't use Celsius. Then that's done now. That's almost done now. Okay, so they asked about the radiation energy from the body. Okay, so now we know the surface area. We know the temperature. So now the dq by dt. So it's epsilon sigma a t to the 4. So if we suppose that this man is a black body, so oh no, it's not actually black. So okay, so if it is a black body, approximately, we have the emissivity of 1, and here the The sigma here is the Stefan-Boltzmann constant. So it is a constant of 5.67 times 10 to the minus 8. So in the unit, so it's quite a difficult unit. Watt per meter square per Kelvin. And for the temperature here, you need to use 303 Kelvin. Okay. In this case, you should be able to find the radiation rate from human. And then for the part B, they ask you about the net rate of heat loss. Okay, so in the part A, the heat rate that you calculate was kind of one-way traffic from human, from the man to the surrounding. But for the net rate of heat loss, in this way, you need to calculate the dq by dt from the dq by dt of a human and minus the dq by dt from the surrounding. So it's gonna be just like this man. He is radiating as usual. But at the same time, and the same man, and the same surface area A, he also got the heat from the surrounding, right? So in this case, for his surface temperature, it is 303, but for the surrounding temperature, it is 20 degrees C or 293 Kelvin. Okay. So in this case, the net rate of heat loss, now it would be epsilon sigma A. So we use the same A. So in this case, it would be the T, the temperature of the man to the 4, minus the temperature of the surrounding of the man to the 4. Okay. So let's see how much have you got for the energy. And then the last questions, example 11. So you do the same thing here, but we are considering the radiation at the sun's surface. Okay? So I really encourage you to calculate like the heat rate from the radiation rate from the example 10 and 11 and try to compare between these two. So you are going to have a feeling about like how many you guys can radiate, right? How much you guys can radiate compared to the sun, right? So man versus sun here. All right. Sorry, they're very same, pretty much the same here, right? So dq by dt is epsilon sigma A T to the 4. But a really huge difference in numbers. Okay, so this constant is the same, emissivity is the same, Stefan-Boltzmann constant is the same, but then the surface area of the sun. So you are given the radius of the sun as about 6.96 times 10 to the 8 meter. So the surface area that you can calculate this from 4 pi r square. So just gonna get something with very large order of magnitude, is at the order of 17. And then for the surface temperature, so what do we have for the surface temperature? We have 300 for surface temperature. But what do the sun have? What does the sun have? The sun have about 6,000 Kelvin for the surface temperature. It is quite intriguing to know that how much the sun's surface, how much is the heat and the radiation at the sun's surface. Okay, so that's gonna be all the stuff here in the handout 10. So see you in the next handout. Have fun. Good luck. Bye.